Hi, I'm Yichao Jin from University of California, Los Angeles. So today I'll be introducing our work in AAAI 2022 towards fine-grained reasoning for fake news detection. This is the joint work with UCLA, Microsoft Research Asia, Hong Kong Baptist University, and Shenzhen University. So first of all, the definition. What is fake news? Fake news is defined as intentionally and verifiably false news published by a news outlet. Fake news is very special because they are usually created intentionally, not accidentally or by some kind of misconception. There are usually people that create fake news because of their own interests or something like that. The widespread of fake news can mislead the public and produce bad social effects or psychological profits for some parties. So that's one motivation why we want to combat fake news. So current works can be split into two major categories. The first category is content-based methods, which mainly utilize the textual or visual content from the news articles for verification. The textual information can include the news article and also the related comments on those articles. The visual content can include the images included in the news article or related videos. The assumption is that fake news usually have a different language style, such as exaggeration or sentimental words or inflammatory descriptions, grammatical mistakes, something like that. And also the images included might be kind of more sensational and may trigger extreme emotions among wide audience. These methods enable early fake news detection because they mainly use the content which is created at the very beginning of the news. But the accuracy might be limited because the news content is only the news content is considered. The examples include support vector machines, gated recurrent unit, RFC, which is random forest classifier, or DTC, which is decision tree classifier. The second category of methods are knowledge-based methods, which mainly utilize external knowledge about the entity relationships or social knowledge about online posts. The assumption is that fake news may also be detected by those auxiliary information, such as how the comments are propagated and also the user features that are behind those user comments. They usually result in higher accuracy, but usually we need to collect more data and the model can be made more complicated because of those extra data. The example models are B trans E, knowledge CNN, GCAN, and also KAN, which is knowledge attention network. The issues about current works are works that approach the task from the perspective of reasoning are still absent. So what is reasoning? Reasoning is the capability of consciously applying knowledge for truth seeking. This ability distinguishes humans from machines, and the reasoning is actually very essential to improve the explainability and accuracy for fake news detection. Oh, for the last word, the last sentence I mentioned is that currently many machine learning methods cannot tactfully leverage the reasoning ability. So reasoning is important because it can jointly improve the explainability and accuracy of the methods. So for explainability, most existing works either do not provide explanations or only enable explainability for a small portion of the neural network, such as the attention layer of the model. If we consciously apply logic to our model, we can understand how the data flow in the model better. The second thing is accuracy. So usually when humans do fact checking, they can do fine-grained analysis to identify subtle clues in the evidence and also the news article to draw conclusions. but existing methods usually overlook those. So this is a motivating example of Barrow's remove from Clinton probability contains body parts from 3 missing women in the 1970s. So if we actually have a glimpse of all the evidence that are or user discussions that are involved in this news, we can see that these discussions can be grouped by under different topics. For evidence that are under certain topics, if we only consider those discussions, we might yield the conclusion that the news is true. But then for other, if we consider other topics and also their kind of in-between relationships or interactions, then we can draw a better conclusion about the truthfulness of the news. For example, in evidence, like in evidence one, evidence group one, such as there are words mentioned such as properties and the words that are more explanatory, through which we can connect different evidence groups, such as DAMN and also go to hell, which are more related to hate speech. And we can also actually by connecting these different evidence groups through these topical words, we can do better fact checking and consider those in-between relationships. So our goal is that we want to move towards using deep learning for fake news detection and jointly improve accuracy and explainability. We ask 3 research questions. So first, can a model be designed by following the human's information processing model? And then can human knowledge about important evidence be better incorporated? And how can we achieve fine-grained modeling of sample clues? So to tackle these research questions, we made 3 contributions. The first one is that we designed a fine-grained reasoning framework for fake news detection, which is FinerFact. Secondly is we proposed a mutual reinforcement-based methods for evidence ranking. And the third one is we designed a prior-aware bi-channel kernel graph network to achieve fine-grained reasoning by modeling different types of subtle clues and decide the importance of each evidence node. So this is the overview of our framework, and actually the entire pipeline corresponds to our first contribution. We can see that our model is split into 2 parts. The first part is the claim evidence graph construction part, which corresponds to the storage subprocess of the human's information processing model. It selects important pieces of information and also build their in-between associations. We can see that there is a mutual reinforcement evidence graph M involved here, which contains 3 types of nodes, which are user nodes, keyword nodes, and post nodes. Keywords are grouped together with respect to the topics that they belong to. And the edges are also constructed according to that. The post nodes are constructed based on the cosine similarities of the posts. And users are connected according to their replying relationships. The second the second part, which is the graph-based fine-grained reasoning framework, corresponds to the retrieval subprocess of the human's information processing model. So it reactivates specific pieces of information based on their associations for decision making. So our the first part corresponds to our second contribution. This part enables us to better incorporate prior human knowledge about which type of evidence are most important. And also by selecting those important information, we can actually filter a lot of noise from the propagation network, so that we can focus on more important information instead of all information. So the first, so this part, for the claim evidence graph construction, the first step is to do mutual reinforcement-based evidence ranking. We actually use attribute saliency to compute a attribute saliency for each node within this network, and we use a PageRank-like methods to propagate the attribute saliency and decide which nodes should be considered more on this graph. And the step 2 is to do mutual reinforcement evidence. So one step is to do mutual reinforcement graph building, and then we do iterative saliency propagation. We can see that actually right here there are 3 graphs involved, which are the post graph P, the user graph U, and also the keyword graph K. And we can choose different beta here to decide how much information to propagate from one subgraph, such as the post graph, to another subgraph, such as the keyword graph. And the second step is to do topic-aware claim evidence association. So in this step, we combine the individual importance of each keyword to decide the importance of each topic. We also do key claim and evidence extraction to retrieve top NT topics with maximum saliency scores, which are computed according to the saliency score of keywords. Finally, we build the claim evidence graph G, which is the graph shown to the right. Each node is composed of a topic T, the sentences ST. For the sentences, I mean the sentences in the news articles, and the PT, which are the online posts related, and also the UT, which are the users that are related to topic T. So those correspond to these actually just constitute the evidence correspond to a topic. And then the third major part is that we design a prior-aware bi-channel kernel graph network to achieve fine-grained reasoning, which is shown to the right. Specifically, this fine-grained reasoning fine-grained reasoning module has 2 components. This first component is node label prediction with bi-channel or kernel matching. This means that we want to use each evidence node to predict a label Y, which is how real this news is. This is indicated by P of Y given V and G. V is a evidence node, and G is the entire graph, and Y is just the binary label of the news. Then the second part is node importance learning with attention priors, which is we want to use the entire graph G and also the mutual ranking score R to predict the importance of a node V. This measures how important this node, the information or the prediction of this node will be. Then this first step is node label prediction with kernel matching. This is actually a very intuitive illustration of how the kernel attention work. So actually each evidence node, the textual information of each evidence node is actually represented as H1, HQ, and HV, something like that. And then we want to compute the pairwise similarity of the tokens within one evidence node to another evidence node. which so the similarity is actually indicated by the orange circle right here in the translation matrix L of Q and V. And then so from the formula, you can see how the attentions are calculated. The alpha QV of I, it actually computes the importance of a token to a new evidence node, and the gamma Q and V actually computes how important the information from from Q is to the actually to the content to the information of V. And then so in the previous slide, we illustrate the text-based reasoning module, and then the user-based reasoning channel works in a similar way, which is that we also use a similar mechanism of our kernel graph attention network to compute the similarity and interactions among users who actually focus on who actually concern different topics. And then part 2 is node label prediction with bi-channel kernel matching. So in this part, we actually use a softmax mechanism and also the prior saliency of each node to compute the importance of each evidence node V. And actually the importance of node V is strongly determined by the information, the matching of news sentences and posts that fall under this current evidence node, and also its attribute saliency. The attribute saliency is actually computed from the information from the mutual reinforcement graph M, which are indicated by RPFT, RUFT, and RKFT. And this is our evaluation. So our evaluation was done on PolitiFact and Gossip Corp. Those are two benchmark data sets for fake news detection. They contain news articles and the social context information about the news. And we also collected some user metadata for our user-based channel. And the labels can be fake or real, which is a binary label. And then the baselines are selected from content-based methods, which are indicated by group G1, and also knowledge-aware methods, which are indicated by G2. And this is the performance chart of our methods. We can see that our kernel-based, kernel attention-based methods can consistently perform better than the two groups of methods. And we also observed that methods that incorporate external knowledge, which fall under G2, is better than those only use the content, which are G1. This illustrates the usefulness of external knowledge in fake news detection. So this is a study of the number of kernels to the performance. We can see that so actually the performance is not very well when we only use a small number of kernels, then gradually increase. But more kernels do not necessarily mean better performance. We observe that the best performance is achieved at a kernel number of around 11 or 10. So this is a case study about how FinerFact reasons about the authenticity of a news story. This is about FBI lawyer Lisa Page disclosing that she was instructed to cover up hacks of the DNC server. So from this case study, FinerFact can successfully identify that the news is fake, and with a detailed explanation about the salient evidence. So the graph, the figure shown to the right is a topic graph with about this piece of news, which is the circled keyword graph in this this figure below. So each color indicates a topic. So we can this is the our case study. So our model actually group different evidence. I mean, the user comments and also the news sentences are below different topics indicated by different color. So actually the grayed out label right here, such as 0.646 / true, is actually a score given by each evidence node indicating how likely this news is true. A higher score means that this this evidence node that belong to this topic predict that this news is more likely to be true. For example, if we only focus on topic the evidence node belonging to topic 1, then this news is more likely to be a true news. However, if we observe the node evidence, the node importance, such as 0.1485, and also the average user salience, which is 0.0018, we can observe that this node should not play a very important role in determining the truthfulness of the news, because the users might not be very credible, and also the model predicts that this evidence node might weigh less in the final prediction. And then if we observe other evidence nodes, such as topic 2, then this evidence node predicts the news to be fake, and also the node evidence, the node importance, and the average user's saliency is relatively high. And by using the kernel graph attention mechanism, we can actually determine the information propagated from one topic to another topic, such as the gray arrow here with the number 0.245. This is the weight of the information that propagates from topic 2 to topic 1. And then we also have the user level attention and also the token level attention, which are given by different node shapes right here. So higher average user score means that the users might express more objective opinions, and the user might be more credible. So the score in the diamond shape is actually the importance of the information that connects different evidence groups through user comments. So these are some of my remaining challenges and thoughts. So currently, many methods still require thorough discussions around multiple topics from the users. This means that if we want to tackle the challenge of early detection of fake news, then we might also consider those lines of works. And also the second point is more about the bias of current fake news detection methods. Are certain entities naturally coupled with fake news during training? Because because many fake news are actually targeting people such as Trump or Hillary or people like those guys. So will the model actually directly predict the news to be fake when they see the words Trump or Hillary. That is still a pending problem. And then thirdly, how to deal with irony, because sometimes humans can actually tell whether a sentence is an irony or not, but machines usually fail to determine. For example, in a news about Trump, which is more about praise of Trump, some users comment, "Wow, Trump is indeed the greatest president in human history." This is indeed ironical, but usually machines just take it as something that is actually praising the guy himself. And then thirdly, fake news has a pleasing effect. They might target specific user groups and creating echo chambers. For example, human might spread fake news because they hope it to be true. But do they actually want to hear the truth? They might just suffering from confirmation bias, in which they are more willing to hear what correspond to their existing opinions. Okay, thank you for listening.